Okay, to pick up where we left off on the in the last section, we were going to go into number 34, and 34 is about nerve impulses in the giant squid, and apparently they travel at about 25 meters per second in speed, and so the book is wondering what is that in feet per second or miles per hour. So let's see, 25.0 meters per second. And let's see if our conversion sheet has anything about feet per second on it. It probably does because engineers used to like that stuff. There we are. 1 meter per second is 3.281 feet per second. Meter per second is, feet per second on top and meters per second on the bottom. 1 meter per second is 3.281 feet per second. And 3.281 times 25 is 82.025 feet per second. And let's see, we have 3 significant figures there and 4 there. So 3 it is. That would be 82.0 feet per second. The next part is going to be a little harder. Well, maybe not, because we probably have that conversion here too. Meters per second to miles per hour. Oh, there we go. 1 meter per second is 2.237 miles per hour. So we can do it in one step. 25.0 meters per second. And we want miles per hour on top and meters per second on the bottom. And it's 1 meter per second is, sorry, 1 meter per second is 2.237 miles per hour. Okay, so meters per second cancel out, and 25 times 2.237 will give us 55.925. And with 3 significant figures, that's 55.9 miles per hour. So that's pretty fast. All right, 30, that was 34. Next, 42. Going to 42, it's about the speed of a glacier. On June 9th, 1983, part of this glacier in Alaska was observed to be moving at a rate of 210 feet per day. That's actually pretty fast for a glacier. Okay, 210 feet per day. What is the speed in meters per second? Okay, in this case, there is no conversion factor on the sheet from between feet per day and meters per second. So we're going to have to do this step by step. In a case like this, where you don't have one conversion factor to take you straight from one unit to another, this is a case where you want to write the unit explicitly as one thing over the other. Instead of writing 210 feet / day, you would write 210 feet over 1 day. This way it makes it clear what's in the numerator and what's in the denominator, and makes it easier to change things to the other units. For the changes, we're going to have to go from feet to meters. And for that, I believe there is a conversion factor in the sheet here. Yeah, 1 meter is 3.281 feet. Okay, so we got that. We can do that in one step. From days to seconds, that's going to be a little harder. How about days to hours to seconds? You could also go days to hours to minutes to seconds, but we'll try to keep it to a minimum. Okay, so Ignoring the bottom unit and just changing the top unit for now, we want it to be meters and we want feet to cancel. There's 1 meter for every 3.281 feet. Okay, feet will cancel and we have meters per day, but we might as well just keep on going. And for days, we want to change that to hours now. Days are in the bottom, so we want that unit on top in the conversion factor so we can get rid of it. And I'm going to count a day as being 24 hours. So now we would have meters per hour if we wanted to stop there and write down the answer. But we want meters per second. And so let's see, hours is on the bottom. There's 1 hour for every 3,600 seconds. That is 60 seconds per minute times 60 minutes per hour. That's 3,600 seconds. And hours should cancel. And now we have units of meters per second. And then we have to work out the numbers though. And that will be 210 divided by 3.281 divided by 24 divided by 3,600. And that's 7.41 times 10 to the minus 4 meters per second. Okay, and let's see. 210 is technically only 2 significant figures, so I guess this should technically be 7.4. Okay, so there we go. And it's a pretty slow speed. I mean, even though 210 feet per day is pretty fast for a glacier, it's still pretty slow overall. All right, from 42, we can go on to 44. So what is the speed in miles? Oh, sorry, miles per second of a beam of light traveling at 3 times 10 to the 8th meters per second? Ah. Oh, this shouldn't be too hard because we just have to change meters to miles. Doubt there's a conversion factor between meters and miles here, but we can go to kilometers and we can change meters to kilometers and there's definitely one between kilometers and miles. So we can try it like that. And the unit on the bottom, we don't have to worry about at all because it's already seconds, which is what we want. What we have is 3.00 times 10 to the 8th meters for every 1 second. And since this is a case where you don't have one conversion factor that will change both units at once, you definitely want to write this as explicitly one thing over the other. So it's 3 times 10 to the 8th meters over 1 second. And we want to go from meters to kilometers. So kilometers goes on top, meters goes on the bottom, and there's 1 kilometer for every 1,000 meters. Now meters cancel, and we would have kilometers per second, but actually we want miles per second. So kilometers go on the bottom. The conversion factor sheet tells us that there's 0.621 miles for every 1 kilometer. Kilometers cancel and we have miles per second. And then we just have to work it out. So 3 times 10 to the 8th divided by 1,000 times 0.621. And we end up with 186,300 miles per second. And that actually is a fairly well-known number. It's often quoted as the speed of light to put it in terms that are more familiar to most people than meters per second. 186. It's usually rounded off to 186,000 miles per second, but it's actually more like 186,300. Okay, let's see. How about 46? A human red blood cell has a mass of about 27 picograms. Okay. The prefix pico means 10 to the minus 12 of a unit. So that's 27. So 27 picograms means 27 times 10 to the minus 12 grams, or in proper scientific notation, that would be 2.7 times 10. And we made this part of the number smaller by moving the decimal point. So you have to make the exponent bigger. That'll be minus 11 grams. So that's the mass of the red blood cell in grams. And what are they actually asking us? What is the mass in kilograms? Okay, so if we have 2.7 times 10 to the minus 11 grams for the mass, then kilograms will just be dividing by 1,000. Okay, so that would be 2.7 times 10 to the minus 14 kilograms. And just to check and make sure I didn't mess anything up. 2.7 times 10 to the minus 11 divided by 1,000. Yep, 2.7 times 10 to the minus 14 kilograms. And let's see, B is, where is it? Nanograms. A nanogram is 10 to the minus 9 grams. Oh, sorry. 1 nanogram is 10 to the minus 9 grams. Okay, so grams cancel, you end up with nanograms, and it's going to be 2.7 times 10 to the minus 11 divided by 10 to the minus 9 equals 0.027. So 0.027 in nanograms. Okay, so not too difficult there. Let's see, number 46, how about 48? Okay, 48 is about mosquitoes. Mosquitoes during their courtship rituals flap their wings at about 605 beats per second. And the question is, how many wing beats occur in a minute? Well, if you have 605 beats per second, and you want to change that to minutes, well, there's 60 seconds per minute. Seconds will now cancel, and beats per minute will be 605 times 60. And so that's 36,300 beats per minute. There is a part B to that question, which I'm not going to do because it brings in the oscillation of a cesium-133 atom, and that's just something way outside anything we really need to know at this point. I don't know where that came from. Number 50 is about the speed of a bullet. The bullet supposedly travels at 4,225 feet per second. And what would that be in miles per hour? Well, once again, feet per second was much beloved by engineers until recently. So that's probably going to be on here, feet per second, and there's miles per hour. When you look for a line that lists both feet per second and miles per hour, you may notice in this case that neither of those numbers is 1, but it doesn't really matter as long as they're equivalent to each other. You can use both numbers. So what we have here is 4,225 feet per second, and the conversion factor sheet tells us that the conversion between feet per second and miles per hour is 2.237 miles per hour for every 3.281 feet per second. Okay, so now feet per second will cancel out and we should get miles per hour. 4,225 times 2.237 divided by 3.281 gives us 2,881 miles per hour. It's actually 2880.6, but rounding it off to 4 significant figures, because this 4,225 is 4 significant figures, and both of the numbers in the conversion factor are 4. So 4 is what we want for the answer, 2881. And I believe there was a part B for this question, and that is, how far in meters can this bullet travel in 5 milliseconds? Well, we've got the original speed, let's see, in feet per second, and we changed that to miles per hour. So we don't really have any metric units for speed. So what we can do, though, is find out how many feet the bullet travels in 5 milliseconds and change that to meters. That would probably be the easiest thing to do. And before then, though, we have to find out how many seconds are in 5 milliseconds. So there's 0.001 second for every 1 millisecond, because a millisecond is 1/1000th of a second. And so that's 0.005 seconds is the time we're talking about. Now, the bullet travels 4,225 feet per second, and in a time of 0.005 seconds, seconds would cancel out and we get feet. 4,225 times 0.005 is 21.13, I'm going to call it. And that's feet. And let's see, 1 meter for every, what is it, 3.281 feet. Okay, so divided by 3.281 gives us 9. 6.439, oh, wait a minute, 5 milliseconds was only two significant figures. So 6.4 would be the number of meters. Okay, so 6.4 meters in 5 milliseconds. Pretty fast. 52 could be useful also. This one has to do with the growth of a baby's brain. They found that the baby's brain grows by 1.6 milligrams per minute. And so the question is, how much does the brain's mass increase in one day? Well, let's see. We've got 1.6 milligrams per minute. We want to change the unit on the bottom to days. Well, I don't know how many minutes are in a day, but we can go from, say, minutes to hours to days. That shouldn't be too bad. There are 60 minutes in 1 hour and 24 hours in 1 day. So let's see, minutes cancel, hours cancel, and we end up with milligrams per day. 1.6 times 60 times 24 gives us 2,304 milligrams per day, or 2.304 grams per day. Okay, so also they want to know how much time does it take for the brain's mass to increase by 0.0075 kilograms. Okay, so 0.0075 kilograms. We've got the rate in milligrams per minute, or grams per day, I suppose, if you want. There's no units mentioned here, so you could use one of these units here, milligrams per day or grams per day, to find out how many days it takes for the brain to increase by this much in mass. Or you could use the original measurement to find out how many minutes it takes, because it just says how long. It doesn't say in what units. In cases like that, I would tend to go with what's given in the problem, just because we may have screwed up the calculations somewhere, which would make this number wrong. So we know that number is right because it was given right in the problem. So if we have milligrams per minute, we're first going to want to know what mass we're looking for in milligrams. So 0.0075 kilograms. First, you want to convert to grams. There are 1,000 grams per kilogram. And then once you're in grams, there's, let's see, 1 milligram for every 0.001 grams. And grams will cancel. Or you could also say 1,000 milligrams per 1 gram. It means the same thing, except writing it this way is more in tune with the definition of what milli means. So 0.0075 times 1,000 divided by 0.001 equals 7,500 milligrams. Okay, so if we've got 7,500 milligrams, that's the mass we want the brain to increase, and it takes 1 minute for every 1.6 milligrams. Then we're basically just using the rate of growth that we were given upside down, and you can do that. There's no reason you can't. So 7,500 divided by 1.6 gives us 4687.5 minutes. For significant figures' sake, let's see, 0.0075 was only 2, as was the 1.6. So we should round this off to 4,700. Remember, the first two digits can stay, but everything from the 8 on has to go. Since 8 is greater than 5, the number before it has to go up by 1, so that's 47. Also, we're dropping 2 digits before the decimal point, so you need to replace those with zeros to maintain the magnitude. So in terms of minutes, it would be 4,700 minutes. You could use other units too if you wanted to, but since no units were specified in the question, any time unit would be okay. And that actually, I think, is the last of the problems in this chapter, in this sort of auxiliary homework problem set that are good for practice. You can look over some of the others, but they're really sort of outside what we need to do. So I'm going to call it here for this lecture, and I'll see if I can find something to do on Monday before our test. But anyway, this will give you a lot of extra practice for the test. Anyway, so see you next time.